Hello everyone, I am Aishwarya, Assistant Professor, Department of Computer Science with Data Analytics. Today we are going to see a topic K-means clustering algorithm. So this is the theoretical overview of this topic. That is the first one we are going to see the unsupervised learning paradigm. So K-means operates on unlabeled datasets to discover intrinsic structures through partitioning without prior training labels. And the next one is objective function. The algorithm aims to minimize the within cluster sum of squares, also known as inertia. And the next one is centroid based model. So this means the clusters are represented by a central vector which serves as the center of mass for all points in that group. And the next one is hard clustering. Unlike fuzzy clustering, every data point in K-means belongs to exactly one cluster, creating distinct boundaries. So next we are going to see the expectation maximization, that is the EM process. Here the step 1 is initialization. So this means the selecting K initial seeds, modern implementation using K-means to ensure an optimized initial spread and foster convergence. And the next step is the assignment process, that means E step. So in this step, each observation is assigned to the cluster within the nearest mean, effectively partitioning the space of Voronoi cells. So step 3 is update, that is the M step. So in this step, the arithmetic mean of all points assigned to a cluster is recalculated and the centroid shifts to this new location. Then step 4 is convergence. So in this step, the process repeats iteratively until the centroid shift falls below a predefined tolerance or assignment stabilize. So the next one is the distance metrics and feature scaling. Here we are going to see the norms that we are calculated for this clustering. So the first one is the Euclidean distance, that is the L2 norm. So the standard geometric distance metric used to measure similarity is, so here the formula will be the distance of P and Q, that is the d of P comma Q is equal to square root of summation Pi minus Qi the whole square. So this is the formula for the L2 norm. And the next one is the Manhattan distance, that is L1 norm. So this means the sum of absolute differences often used in specific high dimensional grid based data sets. And the next one is the necessity of scaling. So in this, K means is isotropic, that is it assumes the features having equal variance. So here the feature scaling using standard scalar is mandatory to prevent features with larger scales from dominating the distance calculation. And the next one is outlier sensitivity. High magnitude outliers can disproportionately pull centroids away from the true cluster center. So next we are going to see the optimal cluster selection, that is we are going to finding the K. So the first method for the optimal cluster selection is the elbow method. So plotting WCSS against the number of clusters to identify the inflection point where the marginal gain in error reduction drops sharply. And the next one is the silhouette analysis, a validation technique that measures how similar a point is to its own cluster compared to others. Here the range varies from -1 to +1. And the next one is the gap statistics. So this compares the total intra-cluster variation for different values of K with their expected values under a null reference distribution. And the next one is Kalinski-Harabas index. So it evaluates the ratio of between the cluster dispersion to within cluster dispersion to determine cluster distinctness. So next one is the algorithm complexity and limitations. Here the limitations are, the first one is the time complexity. So the time complexity is calculated as O, where n is the sample, k is clusters, I is iterations and d is dimensions. It scales linearly with n but struggles with very high d. And the next one is the local optima risk. Results are sensitive to the initial random seeds. Running the algorithm multiple times is the standard fix. Density issues. The next one is the density issues. K means struggles when clusters having significantly different sizes or varying densities. And the next one is the spherical assumption. So in this, the algorithm assumes clusters are spherical and fails on elongated, manifold or ring-shaped data structures. And the next one is advanced enterprise applications. Here the applications are, the first one is the customer segmentation. So in this customer segmentation, behavioral grouping used for personalized marketing, churn prediction and dynamic price sensitivity tiers. And the next one is anomaly detection. Here identifying network instruction or financial fraud by flagging data points that fall statistically far from any cluster centroids. And the next one is the vector quantization. So in the vector quantization applied in image and signal compression to reduce data size while maintaining structural integrity. And the next one is inventory management. So here grouping stock, keeping units based on sales velocity and demand patterns to optimize supply chains. And the next is implementation and best practices. The first one is dimensionality reduction. It always consider a PCA, that is the principal component analysis, before clustering if your dataset has a high feature count that is greater than 20. And the next one is domain integration. The financial choice of K should never rely on statistics alone. It must align with practical business or domain requirements. And the next one is exploratory tool. Here it treats K-means as a powerful first pass algorithm to understand data topology before applying more complex model. And the next one is data preparation. So remember, garbage in, garbage out. Meticulous data cleaning and scaling are more critical than the algorithm's hyperparameters. Thank you.